The morning of August 7th, 1943. Rabaul, New Britain. Imperial Japanese Army Technical Research Institute, Field Assessment Unit. Lieutenant Colonel Takeo Nakamura stood in the maintenance hangar, staring at what should have been impossible. An American M4 Sherman tank sat under harsh electric lights, its hull scorched black from fire, tracks blown off by a Japanese mine near Buna but otherwise intact. The crew had abandoned it during the New Guinea campaign. Japanese forces dragged it 30 miles through the jungle to get it here. 3 months of bureaucratic delays. 2 sunk transport ships. Nakamura had been requesting a captured Sherman since Guadalcanal. Now he had one. But it wasn't the tank itself that held his attention. It was what sat behind him on a steel workbench, surrounded by his engineering team in oil-stained uniforms. The Sherman's engine. A Continental R975 radial. 9 cylinders, arranged in a star pattern, 400 cubic inches of displacement. They'd spent 6 days extracting it from the hull, careful not to damage anything. Another 4 days cleaning it, documenting every component, every measurement. Yesterday, they'd started it for the first time. The sound was different from Japanese engines, smoother, more confident, like it had power in reserve. Nakamura had worked for Mitsubishi Heavy Industries before the war. He'd designed cooling systems for the Type 97 Chiha medium tank. He knew engines. He knew what heat stress looked like, what material fatigue sounded like, what compromised engineering felt like. The Sherman's engine showed none of it. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. His team had run the engine for 4 hours at various throttle settings, full power, idle, everything between. They'd monitored oil pressure, coolant temperature, cylinder head temp, exhaust gas temperature. The engine ran cool, stable, no hot spots, no vibration. Then they'd load it onto a dynamometer to measure actual output. The numbers made no sense. 350 horsepower at 2,400 RPM. Sustained. For the entire test run, the Type 97's Mitsubishi Type 97 diesel produced 170 horsepower, half the output, and the Mitsubishi was considered adequate for a 15-ton tank. The Sherman weighed 30 tons, carried thicker armor, mounted a larger gun, and still moved faster than the Chiha because it had twice the power-to-weight ratio. Nakamura's assistant, Captain Hiroshi Saito, a mechanical engineer from Osaka University, asked the question everyone was thinking. How are they building engines like this? Lieutenant Colonel, our factories can't produce engines at this output level. This represents manufacturing capability we don't have. Nakamura nodded slowly. That's what we're here to determine. Whether this is an isolated example, an experimental unit, or if this represents standard American production. Because if it's standard, if they're mass-producing engines at this specification level, then every assumption we've made about American industrial capacity is wrong. The Imperial Japanese Army had been fighting American forces for 20 months, from Pearl Harbor to Midway to Guadalcanal to New Guinea. Every after-action report mentioned American material superiority, more aircraft, more ships, more supplies. But Japanese doctrine had been built on a different assumption. That Japanese spirit, tactical excellence, and efficient resource use could overcome American material advantages. That willpower mattered more than horsepower. The Sherman's engine suggested otherwise. It suggested that American factories were producing equipment at a sophistication level that couldn't be countered by determination alone. That industrial capacity was destiny, and if that were true, Japan was fighting a war it had already lost. Nakamura ordered comprehensive testing. His team would run this engine until it failed, or until they understood every aspect of its design and construction. They would measure everything, document everything, compare everything to Japanese equivalents, and they would report their findings to Tokyo, even if those findings contradicted what the leadership wanted to hear. Because 23 years earlier, Nakamura had been a junior engineer at Mitsubishi when the company purchased American machine tools to modernize their factory. He'd seen American industrial capability firsthand. He knew what it looked like, and he'd spent the last 2 decades watching Japan build an armaments industry that was sophisticated but small, efficient but fragile, capable but limited. The Continental R975 sitting on that workbench represented something different. It represented the kind of industrial depth that came from decades of automotive mass production, from access to unlimited raw materials, from a manufacturing base that could turn out precision components by the thousands without compromising quality. Nakamura had warned about this before the war, in meetings at Mitsubishi, in reports to the Army Technical Bureau. He'd said that American production capacity was being underestimated, that a war of attrition against an industrial giant would be suicide. His warnings had been noted, then ignored. Japan's leadership believed that a quick, decisive victory would force American surrender before industrial capacity became relevant. Pearl Harbor would cripple the U.S. Pacific Fleet. The Philippines, Malaya, and the Dutch East Indies would fall. America would negotiate peace rather than fight a long war. But the quick victory hadn't happened. The war had become exactly what Nakamura feared, a grinding, attritional struggle where production capacity mattered more than tactical brilliance. And now, standing in a maintenance hangar in Rabaul with a captured American engine, he was about to prove mathematically what he'd always known. Japan couldn't win this kind of war. Testing began in earnest on August 10th. Nakamura's team started with the basics, material analysis. They removed cylinder number 3 for destructive testing. The cylinder was cast aluminum with a steel sleeve pressed into the bore. Under microscopic examination, the aluminum showed uniform grain structure with no visible defects. The steel sleeve was hardened to Rockwell C48, harder than necessary for durability, indicating high-grade steel with no material compromises. Captain Saito ran spectrographic analysis on the aluminum. Silicon content 4.2%, copper 1.8%, magnesium 0.5%. This is high-grade aircraft aluminum, Lieutenant Colonel. The same alloy specification we use for bomber airframes. They're using it for tank engine cylinders. Nakamura made notes. Japan was facing critical aluminum shortages by mid-1943. Aircraft production was prioritized. Tanks got whatever was left over, usually lower-grade castings with higher impurity levels. The Americans were using premium aluminum for a tank engine cylinder. That spoke to resource abundance. Japan couldn't match. The cylinder head was next. Forged aluminum with integral cooling fins and valve seats. The valve seats were beryllium copper alloy, expensive and difficult to machine, but highly resistant to heat and wear. Japanese engines used simpler cast-iron valve seats that wore out faster and required more frequent maintenance. The American design assumed long service intervals. The Japanese design assumed frequent field repairs because that's what limited resources forced. The crankshaft was forged steel, perfectly balanced, with counterweights precisely positioned to minimize vibration. Captain Saito measured runout with a dial indicator. 0.002 inches. Total runout, Lieutenant Colonel. That's exceptional. Our crankshafts typically show 0.005 to 0.01 inches. This is aircraft engine precision in a ground vehicle. The bearings were roller bearings throughout, high-quality steel with precision tolerances. Nakamura examined them under magnification. No pitting, no uneven wear. The engine had been in combat for months in the New Guinea jungle, one of the harshest operating environments imaginable. Mud, water, dust, extreme heat, constant vibration. The bearings showed normal wear, nothing excessive. He compared them to bearings from a Type 97 engine that had been field-stripped after similar service time. The Japanese bearings showed significant wear, scoring on the race surfaces, discoloration from heat stress. The maintenance log showed they'd been replaced twice during the tank's service life. The Sherman's original bearings were still within service tolerance after longer use in worse conditions. The cooling system revealed more disparities. The Sherman used a pressurized radiator system with a 15 psi cap, Higher pressure raised the boiling point of the coolant, allowing the engine to run hotter without overheating. Japanese tanks used unpressurized systems that boiled over more easily in tropical conditions. The Sherman's radiator was copper and brass throughout, no steel substitutes, no corrosion visible. Japanese radiators increasingly used mild steel with copper plating to save strategic materials. The plating wore through quickly, causing leaks and corrosion failures. But the most telling component was the oil pump. The Sherman's pump was gear-driven from the crankshaft, with hardened steel gears and a bronze housing. At full throttle, it delivered oil pressure at 60 psi, ensuring adequate lubrication, even under extreme loads. The Type 97's pump delivered 35 psi maximum. Under hard use, in high heat, oil pressure would drop below safe levels, causing accelerated wear and eventual failure. Nakamura compiled the material analysis into a preliminary report. Every component showed evidence of high-grade materials, precision manufacturing, and design margins that prioritized reliability over resource efficiency. There were no shortcuts, no compromises, no substitutions forced by material scarcity. The engine was built the way engineers would build it if resources were unlimited. Because, for America, resources were unlimited. On August 15th, the team began endurance testing. They'd run the engine on the dynamometer continuously, measuring how long it could operate before failure. Japanese Type 97 engines typically required major maintenance after 400 hours of operation. Cylinder sleeves wore out, bearings failed, cooling systems developed leaks. The engines were adequate for their design life, but they weren't built for sustained hard use. The test protocol was simple. Run the Sherman's engine at 70% throttle, roughly 250 horsepower output, simulating combat conditions. Monitor all temperatures and pressures. Run it until something breaks. Nakamura estimated they'd get maybe 600 hours before major maintenance was required. The Americans had more resources, better materials, tighter tolerances. Surely that translated to maybe 50% better endurance. The engine ran for 100 hours without incident. Oil pressure is steady at 55 psi. Coolant temperature stable at 180 degrees Fahrenheit. Exhaust gas temperature nominal. No unusual vibrations. No oil consumption beyond normal. At 200 hours, Captain Saito checked the oil. Clean. No metal particles indicating wear. The oil filter was cut open and examined. Minimal debris. The engine was barely wearing in. At 300 hours, they performed a detailed inspection, removed the cylinder heads, measured cylinder bore wear with a telescoping gauge. 0.003 inches of wear across all cylinders. Negligible. Checked valve clearances. Still within specification. Examined the bearings. Normal wear pattern. No distress. The engine looked like it had hundreds of hours of life remaining. At 400 hours, the milestone where Japanese engines required major maintenance, the Sherman's engine showed no signs of distress. They kept running it. At 500 hours, a Japanese Army observer from Tokyo arrived to witness the testing. Colonel Kenji Matsumoto, Deputy Director of the Army Technical Bureau. He'd been skeptical of Nakamura's preliminary reports. Material superiority was one thing, but Japanese engines were combat-proven, reliable. This American engine was probably a cherry-picked example, not representative of production standards. Matsumoto watched the dynamometer readout. 250 horsepower. Steady. The engine had been running continuously for 23 days. How much longer do you expect it to run, Lieutenant Colonel Nakamura? Nakamura shook his head. I don't know, sir. Our Type 97 would have failed by now. This engine shows no indication of impending failure. We'll continue testing until something breaks or until we reach our operational limits. What are your operational limits? Fuel. We have enough gasoline for another 400 hours of testing. After that, we'll need resupply, which, given current logistics constraints, may not be possible. Matsumoto looked at the engine, then at Nakamura. You're telling me this American engine could run for 900 total hours? I'm telling you, it hasn't failed yet at 500 hours, when our equivalent would have required a complete rebuild at 400. Whether it reaches 900 hours, I don't know. But every hour it continues to run, is an hour beyond what the Japanese industry can currently produce. The engine ran for 600 hours. 700. At 800 hours, oil consumption began to increase slightly, from half a quart per 10 hours to 3/4 of a quart, still acceptable, but indicating that ring wear was progressing. Compression checks showed minor loss in 2 cylinders, from 130 psi to 120 psi. The engine was wearing, but gradually, predictably, with no catastrophic failures. At 900 hours, they shut it down. Not because it had failed, but because they'd exhausted their fuel supply. 37 days of continuous operation at 70% throttle. Final inspection showed cylinder bore wear of 0.012 inches, bearing wear within acceptable limits, no cracks in the crankshaft or connecting rods, no head gasket leaks, no cooling system failures. The engine could be reassembled and returned to service with minor parts replacement. Nakamura stood in the silent hangar. The dynamometer was cold now, the engine sitting on the workbench surrounded by measurement equipment. 900 hours, more than twice the service life of a Japanese engine. And it hadn't failed. It had simply run out of fuel. Captain Saito spoke quietly. Lieutenant Colonel, I've calculated the equivalent operational readiness. If Type 97 engines require major maintenance every 400 hours and Sherman engines run 900 hours, the Americans need half as many spare engines to maintain the same number of operational tanks. Their logistics burden is half of ours for the same combat effectiveness. Nakamura nodded. And their tanks start with twice the horsepower, so they're more combat effective to begin with. We're not just behind in engine life, we're behind in every measurable category. Power output, reliability, maintainability, material quality. There's no category where the Type 97 is superior. But the endurance test had revealed something beyond component quality. It revealed a design philosophy. The Sherman's engine wasn't built to barely meet requirements. It was built with massive safety margins, overbuilt, over-engineered. The crankshaft was stronger than necessary. The bearings were larger than required. The cooling system had more capacity than the engine needed. Every component had reserve capacity, which meant the engine could handle abuse, neglect, harsh conditions, and keep running. Japanese engines were built at the edge of what was technically possible. Every component was optimized to save weight, save materials, and save cost. There was no margin for error. If a crew neglected maintenance, if operating conditions exceeded design parameters, if inferior fuel was used, the engine failed. The American approach was brutally effective. Build it strong enough that it forgives mistakes. Build it reliable enough that logistics become easier. Build it powerful enough that tactics become more flexible. Nakamura requested production data from intelligence sources. What he learned was devastating. The Continental R975 wasn't designed for the Sherman. It was an aircraft engine from the 1930s, used in trainers and light aircraft. When America needed a tank engine quickly, they adapted an existing design that was already in mass production. No development time, no tooling delays. They took an off-the-shelf aircraft engine and put it in a tank, and it worked better than purpose-designed Japanese tank engines because the American automotive and aircraft industries had spent decades refining high-volume production techniques, developing sophisticated alloys, training skilled workers, building supply chains. The R975 represented accumulated industrial knowledge going back to the Model T Ford. Japan had nothing equivalent. Japanese automotive production before the war was tiny, maybe 30,000 vehicles per year total. America produced millions. The manufacturing base, the supplier network, the engineering expertise, all favored America by orders of magnitude. But the production numbers were even more crushing. Intelligence reports indicated America was building Sherman tanks at a rate exceeding 2,000 per month, over 24,000 per year. Japan's entire production of medium tanks for 1943 would be roughly 1,000 vehicles total. America was building 24 times more tanks, and each American tank was more powerful, more reliable, better armored than its Japanese equivalent. The R975 engine wasn't just used in Shermans. It powered the M2 light tank, the M3 Lee, various armored vehicles, total production would exceed 50,000 units during the war. Japan's entire production of tank engines across all types would be maybe 15,000. America was building 3 times more of a single advanced engine than Japan could produce total engines of all types. Nakamura sat at his desk in the hangar office, staring at intelligence summaries and production estimates. The mathematics were undeniable. He'd run them multiple times, thinking he'd made errors. But the numbers didn't change. American tank production for 1943 was projected to exceed 29,000 vehicles. Japanese production would be approximately 1,500, a ratio of 19-1, and American tanks were individually superior. The material disparity wasn't just in tanks. Intelligence showed America producing over 85,000 aircraft in 1943. Japan would produce 16,000. American shipyards were launching aircraft carriers at a rate of 1 every 6 weeks. Liberty ship freighters at a rate of 3 per day. The industrial mobilization was beyond anything Japanese planners had anticipated. America wasn't just outproducing Japan. It was outproducing Japan, Germany, and Italy combined, while simultaneously supplying Britain, the Soviet Union, and China. Nakamura's final report was due to be forwarded to Tokyo. As he compiled his findings, he knew he was writing something that would be seen as defeatist. The report documented the Sherman's technical superiority in multiple areas. It acknowledged that Japan lacked the industrial capacity and material resources to produce equivalent engines, and it contained a conclusion that contradicted official optimism about Japan's strategic position. His summary read, "The Continental R975 engine represents a level of industrial sophistication and resource abundance that exceeds Japan's current and projected capabilities. Its widespread deployment in multiple vehicle types suggests American production capacity far exceeds previous intelligence estimates. The engine's reliability and power output provide American forces with significant tactical advantages that cannot be countered through superior training or tactics alone." Recommendation: strategic reassessment of Japan's ability to sustain prolonged mechanized warfare against an opponent with overwhelming material superiority. In other words, we're losing an industrial war to an enemy whose production capacity makes victory impossible through conventional means. Colonel Matsumoto, who'd stayed at Rabaul to observe the full testing program, read the report and looked at Nakamura with concern. "This will not be well received in Tokyo. The General Staff believes American industrial capacity, while substantial, can be overcome through operational excellence and fighting spirit. Your report suggests that's impossible." "Should I alter my findings, sir?" Matsumoto was quiet for a long moment. "No, the data is accurate. The conclusions are sound. But prepare yourself for criticism. The leadership has committed Japan to a strategy that assumes material disadvantages can be overcome. Your report challenges that assumption. Men who've built careers on that strategy will not abandon it based on one engineer's analysis of one captured engine, no matter how compelling the evidence." The report was transmitted to Tokyo via encrypted naval communication. Nakamura never received an official response, but through informal channels he heard that it had been read by senior staff officers and largely dismissed. One general reportedly said the report showed excessive deference to American engineering and insufficient confidence in Japanese capabilities. Another called it technically interesting but strategically irrelevant because Japan's war strategy was based on defensive perimeters and attrition, not mechanized warfare. Nakamura wasn't surprised. He'd seen this pattern throughout his career. Technical reality subordinated to institutional preference. Data dismissed when it contradicted doctrine. Engineers providing accurate assessments, then watching as those assessments were ignored because they implied uncomfortable truths. But for Nakamura personally, the examination of the Sherman's engine had been revelatory, not just about the engine, but about the war. In the months following his report, Nakamura watched his predictions come true. American tanks appeared in increasing numbers across the Pacific. Japanese anti-tank weapons, designed to fight lighter vehicles, were inadequate against Sherman armor. Tank battles became one-sided massacres. Experienced crews were killed and not replaced because Japan couldn't produce enough tanks to train replacements. These strategic recommendations he'd made, avoiding tank-on-tank engagements and using infiltration tactics instead, were gradually adopted. But by then, American material superiority was so overwhelming that tactical adjustments made little difference. The United States had achieved material dominance through sheer weight of production. Every island Japan defended faced naval bombardment from unlimited ammunition, airstrikes from unlimited aircraft, and ground assault supported by vehicles Japan couldn't match or replace. Nakamura examined other captured American equipment as it became available. A Caterpillar D8 bulldozer used by Navy Seabees to build airfields. It was powered by a diesel engine, producing 135 horsepower, ran reliably in all conditions, and represented engineering sophistication Japan's construction equipment industry couldn't match. A GMC truck, one of hundreds of thousands, produced with a 6-cylinder engine, 4-wheel drive, and payload capacity that exceeded Japanese equivalents by 30%. Every piece of equipment told the same story: superior materials, sophisticated engineering, evidence of an industrial base operating at a scale Japan had never achieved and never would. What haunted Nakamura was that this information should have been available before the war. Japanese military attachés had visited American factories. Intelligence officers had reported on American production. Trade data showed American industrial output. But the leadership had either not believed the reports or had believed that Japanese spirit could overcome material disadvantage. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Nakamura had been trained as an engineer at Tokyo Imperial University. He believed in mathematics, in physical reality, in empirical data, and the physical reality was undeniable. Japan was fighting an industrial war against an enemy with 10 times the production capacity, unlimited raw materials, and engineering sophistication built over decades of civilian industrial development. The Sherman's engine was proof. 900 hours of operation when Japanese engines failed at 400. Twice the horsepower from a more reliable package using materials Japan couldn't source in sufficient quantities. After the war, when production figures were declassified, Nakamura's estimates were proven conservative. He'd underestimated American capacity. Total American armored vehicle production from 1940 to 1945, over 115,000 vehicles. Japanese production in the same period, approximately 6,800. America produced 17 times more armored vehicles. The Sherman alone, 49,761 units produced. More than Japan produced tanks, trucks, and armored cars combined. The Continental R975 engine that Nakamura had tested with such methodical precision, over 50,000 units produced, not by a specialized military factory, but by Continental Motors, an automotive supplier in Muskegon, Michigan. They'd converted from building car engines to building tank engines, retooled in months, and reached full production in less than a year. Japan had no equivalent industrial flexibility, no vast automotive sector that could be converted to war production, no supplier base that could scale up on demand. The war had been lost before it started, lost in the factories and engineering schools and steel mills of the American industrial heartland. Men like Nakamura had known about it, had tried to warn about it, and had been ignored because the truth was too uncomfortable to accept. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe. I'll continue expanding the script with additional content. November 1943. Nakamura received a new assignment, a Type 97 Chiha had been recovered from a failed counterattack near Finschhafen. The tank had traveled only 420 miles, according to the engine log, before catastrophic overheating caused the crew to abandon it. The engine had seized completely, the pistons welded to the cylinder walls by heat. It wasn't unusual. Field maintenance reports showed similar failures across multiple units. Nakamura had designed the cooling system for this engine back in 1937. He knew its limitations, but he'd never directly compared it to an American equivalent under identical test conditions. Now he would. The Type 97 engine sat on the workbench next to where the Sherman's Continental had been tested. The contrast was immediate. The Japanese engine was smaller, more compact, inline, six-cylinder diesel, 170 horsepower rated output. It looked efficient, purposeful, designed to exact specifications with no wasted space or excess material. Captain Saito prepared the dynamometer for a parallel endurance test. They would run the Type 97 under the same conditions they'd used for the Sherman engine, 70% throttle, continuous operation, monitor all parameters until failure. Nakamura already knew what would happen. He'd written the maintenance schedules, 400 hours to major overhaul, but he needed documentation. He needed photographs and measurements and temperature data that would prove what he already understood. The test began November 18th. The engine started easily, settled into a steady rhythm. 120 horsepower output at 70% throttle, oil pressure 32 psi. Coolant temperature climbed to 195 degrees Fahrenheit, 15 degrees hotter than the Sherman's engine had run. Within normal parameters, but close to the edge. At 50 hours, oil consumption was noticeable, 1 quart every 8 hours. The Sherman had used 1 quart every 20 hours at the same point in testing. The Japanese engine was burning oil, which meant the piston rings were wearing faster, allowing combustion gases to blow past into the crankcase. At 100 hours, coolant temperature began creeping upward. 198 degrees, 200, 203. The engine was running hotter as internal wear increased friction and reduced efficiency. Captain Saito monitored the gauges with growing concern. Lieutenant Colonel, if this continues, we'll see boiling within another 50 hours. The cooling system is losing capacity. Nakamura nodded. He'd seen this pattern in field reports. The Type 97's cooling system had minimal reserve capacity. As the engine wore, as tolerances opened up, as friction increased, the cooling system couldn't compensate. The temperature climbed until the engine destroyed itself. At 150 hours, they discovered the first serious problem: metal particles in the oil. The filter was cut open and examined, bearing material. The connecting rod bearings were wearing rapidly, shedding bronze particles into the lubricating oil. The oil pressure had dropped to 28 psi, below the minimum safe threshold. They replaced the oil and filter, documented the failure, and continued testing. At 200 hours, the number 2 cylinder was losing compression, down from 110 psi to 90 psi. The piston rings were worn or possibly broken. Blow-by gases were contaminating the oil, turning it black and acidic. They changed the oil again, noted the compression loss, and kept running. At 250 hours, coolant temperature reached 212 degrees Fahrenheit. Boiling. Steam vented from the overflow tank. They shut down the engine, let it cool, topped off the coolant, and restarted. Within 30 minutes, it was boiling again. The cooling system had lost the battle against internal heat generation. At 300 hours, bearing noise became audible, a rhythmic knocking from deep in the engine, synchronous with crankshaft rotation. The connecting rod bearings were failing completely. Oil pressure was down to 23 psi. Multiple cylinders showed low compression. Coolant was boiling continuously, requiring makeup water every 2 hours. At 340 hours, the engine seized. No warning. No gradual degradation. The crankshaft locked solid mid-rotation. The dynamometer's emergency brake engaged. The sudden stop bent a connecting rod. When they disassembled the engine, they found bearing number 3 had completely disintegrated. Bronze bearing material had welded itself to the crankshaft journal. The piston for that cylinder had tried to continue moving, bent the connecting rod, jammed the crankshaft. Nakamura supervised the teardown with methodical precision. Every component was measured, photographed, analyzed. The cylinder bores showed scoring where the piston rings had worn through. 0.025 inches of wear in 340 hours. 3 times worse than the Sherman's bore wear at 900 hours. The crankshaft journals showed heat discoloration and galling where the bearings had failed. The cylinder head had warped from sustained overheating, causing head gasket leaks that allowed combustion gases to enter the cooling system, which explained the accelerated coolant loss. Captain Saito laid out the failed components like pieces of a dissected corpse. The Sherman ran 900 hours with minimal wear. Our Type 97 failed catastrophically at 340 hours. That's a durability ratio of 2.6 to 1, and the Sherman started with twice the horsepower. Nakamura made detailed notes for his supplemental report, but beyond the numbers, beyond the measurements, the comparison revealed something more fundamental. The Type 97 wasn't a bad engine. It was a competent design, executed with limited resources. The problem was that I wasn't enough, not against an opponent who could field engines with twice the power and 3 times the reliability. He thought about tank crews in the field, Japanese tankers who'd been told their Type 97 Chiha was adequate for combat, who'd been trained to believe that tactical skill could overcome material disadvantages. What happened when those crews encountered Shermans, when their 170 horsepower engine faced an enemy's 350 horsepower, when their tank broke down after 400 miles while the enemy's tank was just getting broken in? The mathematics were brutal. If Japanese tanks required 3 times more maintenance, Japan needed 3 times more spare parts, 3 times more mechanics, 3 times more logistics support to field the same number of operational vehicles. But Japan didn't have 3 times more resources. Japan was already struggling to maintain minimal production levels with dwindling raw material stockpiles and increasing disruption from American submarine warfare. December 1943. Nakamura compiled his supplemental report. He included side-by-side photographs. The Sherman's engine after 900 hours, components showing normal wear, ready for minor service and return to duty. The Type 97 after 340 hours, catastrophically failed, requiring complete rebuild with new crankshaft, bearings, pistons and cylinder head. He included comparative data tables, power output, durability, material quality, manufacturing precision, maintenance requirements. Every metric favored the American engine, some by small margins, some by factors of 2 or 3. The supplemental report concluded, direct comparison testing confirms that American tank engines possess substantial advantages in power output, reliability, and service life. Japanese Type 97 engines, while adequate for their original design parameters, are insufficient for sustained mechanized warfare against an opponent with superior industrial capacity. The durability disparity means Japanese forces require approximately 3 times the logistics support to maintain equivalent operational readiness. Given current resource constraints and supply line vulnerabilities, this disparity will result in decreasing Japanese armor effectiveness over time. He forwarded the report through Colonel Matsumoto. 2 weeks later, he received an official response for the first time. Not an acknowledgement or a request for clarification. A reprimand. His report had been reviewed by the Army Technical Bureau. The findings were noted, but the conclusions were deemed excessively pessimistic and potentially damaging to morale. He was instructed to focus future assessments on identifying exploitable weaknesses in American equipment rather than documenting Japanese inadequacies. Nakamura read the reprimand twice. The language was bureaucratic, but the message was clear. Stop telling us things we don't want to hear. The technical data was undeniable. The photographs showed failed components. The measurements proved inferior performance. But institutional momentum was more powerful than evidence. Japan's leadership had committed to a strategy. Contradictory data wouldn't change that strategy. It would simply be ignored. January 1944. American forces landed at Sidor, cutting off Japanese positions along the New Guinea coast. Rabaul was being bypassed, isolated, and bombed daily. Supply ships stopped coming. The captured Sherman sat in the hangar gathering dust, a monument to industrial capacity Japan couldn't match. Nakamura and his team were eventually evacuated to Truk, then to the Philippines as American forces advanced. He continued his technical work throughout 1944, analyzing captured equipment when available, writing reports that went unread, watching as Japanese armor forces were systematically destroyed in battle after battle. Saipan, Peleliu, Leyte, every engagement followed the same pattern. Japanese tanks, outnumbered and outgunned, tried to fight American Shermans with equipment that couldn't compete. Tactics and courage couldn't overcome a 2-to-1 power disadvantage and 3-to-1 reliability disadvantage. August 1944. Philippines. Nakamura received intelligence reports from the Marianas. American forces had captured hundreds of Japanese tanks on Saipan, mostly Type 97s, some Type 95, light tanks. The Americans were conducting their own technical evaluations. Nakamura wondered what their engineers would conclude. Probably the same things he'd concluded about the Sherman, that the enemy's equipment was superior in every measurable way. But there was a difference. American commanders would receive those reports and know their equipment was adequate. Japanese commanders received Nakamura's reports and chose to disbelieve them. One side used technical intelligence to refine tactics and maintain confidence. The other side rejected technical intelligence that contradicted pre-war assumptions. October 1944, Battle of Leyte Gulf. Japan committed its remaining naval forces in a desperate gamble. The fleet was decimated. American industrial capacity had replaced every ship lost at Pearl Harbor and built hundreds more. Japan's shipyards couldn't replace losses, couldn't even maintain existing ships properly due to parts shortages. The same pattern as the tank engines. America is building faster than Japan could destroy, Japan losing faster than it could replace. The war had become exactly what Nakamura had feared when he examined that Continental R975 engine back in Rabaul. A mathematical certainty, an industrial equation with only one solution. November 1944, American bombers began systematic attacks on Japanese cities, B-29 superfortresses flying from the Marianas. Each bomber was powered by 4 Wright R-3350 engines. Each engine produced 2,200 horsepower, more powerful than the Continental R975, more powerful than any engine Japan had ever produced. Nakamura thought about that. America was building 4-engine bombers, with engines more advanced than what he'd tested, building them in quantities that allowed sustained strategic bombing campaigns. Each B-29 represented industrial capacity, equivalent to producing multiple Japanese tanks, and America was building hundreds of them, while simultaneously building thousands of fighters, thousands of tanks, hundreds of ships. The numbers had stopped being surprising. They'd crossed into absurdity, into mathematical realities so extreme they felt fictional. But they were real. Nakamura had touched the evidence, had measured the components, had watched the Sherman's engine run for 900 hours when Japanese engines failed at 340. The physical proof was undeniable. The war was lost, had been lost since 1942, when America's industrial mobilization reached full capacity. Everything since then was just the slow, grinding mathematics of production capacity, overwhelming tactical excellence. March 1945, American forces landed on Okinawa. Japanese armor forces committed their last operational tanks, Type 97s, Type 3 Chinus, Type 4 Cheetos, the newest Japanese designs with improved armor and 75mm guns, better than the 1937 vintage Type 97, but still inadequate against Shermans that had also improved. The Americans were fielding M4A3 models with 76mm high-velocity guns, wet ammunition storage, and improved armor. And they had hundreds of them. Japan had dozens. The battle lasted 3 months. Every Japanese tank was destroyed. Everyone. Nakamura heard the casualty reports, watched the lists of dead tankers, young men who'd believed Japanese spirit could overcome American steel. who trusted that their training and determination mattered more than horsepower and armor thickness. They'd been wrong, and they'd died for that mistake. August 6th, 1945, Hiroshima. August 9th, Nagasaki. The atomic bombs represented the ultimate expression of what Nakamura had discovered in Rabaul. Industrial and scientific capacity was so overwhelming it could literally reshape the physics of warfare. America hadn't just outproduced Japan in tanks and aircraft, it had developed weapons that made conventional military strength irrelevant. August 15th, Japan surrendered. September 1945, American occupation forces arrived in Tokyo. Nakamura was interviewed by U.S. Army technical intelligence officers. They'd found his reports in captured Japanese military archives. They were particularly interested in his 1943 analysis of the Sherman's engine. Lieutenant Colonel Nakamura, your report accurately identified American industrial advantages 2 years before Japan's surrender. Did other Japanese officers reach similar conclusions? Nakamura considered the question carefully. Many technical officers understood the industrial disparity. Metallurgists knew we lacked strategic materials. Factory managers knew production rates were inadequate. Intelligence officers reported American output figures. The information existed, but institutional culture prevented it from influencing strategic decisions. Why? Because accepting the data meant accepting that the war was unwinnable. Japanese military culture was built on the premise that will and spirit could overcome material disadvantage. That superior tactics and fighting determination mattered more than industrial capacity. To accept that American production made victory impossible would have been to admit the war should never have been started. The leadership couldn't accept that, so they rejected the evidence. The American officer nodded slowly. We found your report from November 1943, the one where you directly compared the Sherman engine to your Type 97, 900 hours versus 340 hours of operational life. That's a devastating disparity. Yes, I hoped that specific comparison would force recognition of the problem. It didn't. I received a reprimand for excessive pessimism. Did you believe Japan could still win at that point? Nakamura shook his head. No. The mathematics were clear by mid-1943. America was producing 20 times more armored vehicles, 5 times more aircraft, unlimited ammunition and fuel. Japan's supply lines were being destroyed by submarines. Raw material stockpiles were depleting. Industrial capacity was declining due to bombing and resource scarcity. The only question was how long Japan could sustain resistance, not whether victory was possible. The American officer made notes. Your analysis was accurate. U.S. industrial production for the war totaled over $300 billion in military equipment, 2/3 of all Allied production. We outproduced all Axis powers combined. After the interview, Nakamura walked through Tokyo's ruins. Entire neighborhoods burned to ashes, factories destroyed, ports demolished, the physical manifestation of what he'd understood abstractly in 1943. Industrial capacity determines strategic outcomes. America's factories are producing faster than Japan could destroy. Japan's cities are burning faster than defenders could rebuild. He thought about the Continental R975 engine, 900 hours of operation, reliable, powerful, built with unlimited access to strategic materials and precision manufacturing. The engine had been a prophecy, a physical proof of industrial advantages that would grind Japan into defeat. He'd documented the evidence, written the reports, tried to warn the leadership, and been ignored because the truth was too uncomfortable to accept. Years later, Nakamura would write a technical memoir. He titled it Horsepower in History: How Production Capacity Determined the Pacific War. The book included the original photographs from Rabaul, the Sherman's engine after 900 hours, the Type 97's catastrophic failure at 340 hours, the comparative data tables, the intelligence estimates of American production that proved conservative. In the introduction, he wrote, "As an engineer, I was trained to trust empirical data above institutional assumptions. In August 1943, I examined a captured American tank engine. The evidence it provided was mathematically conclusive. Japan was fighting an industrial war against an opponent whose production capacity made conventional military victory impossible. I reported these findings. They were dismissed. 2 years and millions of casualties later, the war ended exactly as the mathematics predicted it would. The lesson is not about engines or tanks. It is about the cost of rejecting evidence that contradicts preferred narratives, about the danger of subordinating technical reality to ideological commitment. The Continental R975 engine ran for 900 hours because American industry could build it that well. The Type 97 failed at 340 hours because Japanese industry couldn't match that standard with available resources. That disparity determined strategic outcomes more than any tactical brilliance or fighting spirit ever could. We ignored the evidence, and millions paid the price for that willful blindness. The book was published in 1953. It sold modestly in Japan, where veterans groups criticized it as defeatist. It was translated into English in 1956 and became required reading at the U.S. Army Armor School. American officers studied it as a case study in technical intelligence and industrial warfare. The lesson they drew was simple. Material capacity matters. Production determines outcomes. Evidence defeats mythology. Every time. Nakamura died in 1978. By then, Japan had rebuilt as an industrial power, this time focused on civilian manufacturing. Toyota, Honda, Mitsubishi. The automotive industry Japan lacked in 1941 had become world-leading by the 1970s. Japanese engines had become synonymous with reliability and precision. The capacity that couldn't be mobilized for war had flourished in peace. His obituary in the Asahi Shimbun noted his technical contributions, but it also quoted from his memoir, "I measured the engine that proved Japan had lost the war. I reported the findings. I was ignored. That is my legacy. Not the measurements, but the institutional failure to act on evidence. May future generations learn that lesson better than mine." He did. The Continental R975 engine Nakamura tested in Rabaul was never recovered. It was abandoned when American forces bypassed the base, presumably destroyed or left to rust in the jungle. But its legacy endured. In the technical reports that documented American industrial superiority, in the training manuals that taught the value of reliability and power, in the historical understanding that World War II was, fundamentally, an industrial war where production capacity determined outcomes more than tactical brilliance ever could. And in the lesson that evidence matters, those measurements don't lie. That when an engineer tests an engine and discovers his nation's equipment is inferior by a factor of 3, that information should be treated as strategic intelligence, not institutional embarrassment. Takeo Nakamura tested a captured Sherman engine for 900 hours, watched it run continuously for 37 days without failure, compared it to Japanese engines that failed at 340 hours, and reported that Japan couldn't win an industrial war against an opponent with that level of production sophistication. He was right. The mathematics proved it. The battlefield confirmed it. The rubble of Tokyo testified to it. One captured engine, one methodical engineer, one accurate report that was ignored, and millions of casualties that might have been prevented if evidence had been trusted over ideology. That's the legacy. The reminder that in war, as in engineering, reality doesn't care what you believe. It only cares what's true.